When we discussed about push down automata, we saw that what we defined is a non-deterministic push down automata. Today, we shall first see or recollect why the automata that we defined with the stack as an intermediate storage is not to be a non-deterministic push down automata. After that, we shall define what is called a deterministic push down automata. And unlike in the case of finite state automata, non-deterministic push down automata are strictly more powerful than deterministic push down automata. We shall see a language for which there is no deterministic push down automaton exists, but we already have designed a non-deterministic push down automaton. So let us move on to the topic for today, which is deterministic push down automata. So we can try to answer this question before we go and see what are deterministic push down automata. In what sense PDAs we discussed are non-deterministic? Consider a push down automaton with this configuration. So this configuration tells the current state is P, the unprocessed part of input is BAB, and the content of the stack is A bottom. So this is the configuration. In the configuration, we have the current state, the unread part of the input. We are not considering the part of the input which is already processed, the remaining part, and the content of the stack. Now suppose you have these two transitions in this automaton. Now you are in the state P, you are reading the input symbol small b, and capital A is on top of stack, and for that two different transitions are defined. If you apply the first transition, this is what is going to happen. Anyway, you will move to the next symbol in the input tape, and the first transition is asking you to change your state to Q and replace capital A with capital B. So this is what is happening if you apply the first transition. And if you apply the second, this is the next configuration. What is it? You are changing your state to Q, and this symbol is processed, so the remaining part is AB, and what is on the stack is B bottom. And if you apply the second transition, this is what is happening, and the configuration is this. The state is R because you are asked to move on to R. The next component is the remaining part of input, that is true. Sorry, that is same for both because you are moving to the next in both the cases. And here the content of the stack is brought along because you are only popping capital A, not pushing anything. Thus you can see that in this case, if you are coming to this configuration, the next configuration is not uniquely defined. It can be any one of these two based on which transition you are going to apply. And the automaton is assumed to have the power to non-deterministically select one of these two, just like in the case of a non-deterministic finite state automaton. That is case 1 where you can have non-determinism. Now you consider the same configuration where you have two transitions. One is defined when the current state is P, the current input symbol is B, and the top of stack symbol is capital A. So here the current state is P, the next input symbol to be processed is small b, and the top of stack symbol is capital A. So the first transition applies, and now you can see that what is the second transition? It says if P is the current state, then without reading the next input symbol, so it does not matter what it is, and if capital A is on the top of stack, you can apply this. In that case, you are asked to change to small r. So here as well, you have two possibilities, and if you apply the first, this is the configuration that you are getting. You can verify it offline, and if you apply the second transition, this is what you are getting. So here again, the next configuration is not uniquely defined. So there are two cases. One is for the same input symbol and the same top of stack for a given state, two transitions are defined. That is non-determinism. Or one transition is there for the next symbol, and also there is an epsilon transition which can also be applied. So in any of these two cases, the next configuration is not uniquely defined. In one step, you can either move into this configuration or into this, depending on which transition you are applying. Now, we can see how we can model the computation of a PDA. You know that for any PDA, the initial configuration is this. The state is the start state, the entire input string needs to be processed and only bought on the stack as its content. So this is going to be the unique initial configuration for any push down automaton with input W. If the input is W, then this is the configuration. Always the start state and just bought on the stack. Now we saw that from this configuration there could be multiple next configuration possible. So this is one, maybe you have this transition, you can see what that transition is, or you can have another transition leading to this, maybe yet another one. So there may be finitely many next configurations possible, and this is non-determinism because next configuration is not uniquely defined. And from here as well, maybe there are two possibilities. Here one possibility, it goes like this. Thus, the computation of a PDA, when I say PDA, I mean non-deterministic PDA, can be modeled as a tree. An input is said to be accepted if there exists an accepting path originating at the root node. If one of these paths is accepting, depending on the acceptance criterion that you are selecting, if one of the path is accepting, then the input is said to be accepted. So in the case of a non-deterministic push down automaton, the computation on a given string can be modeled as a tree. Now we can see what is a deterministic push down automaton. So basically here the computation is going to be a sequence of states. Every time the next configuration is uniquely defined. If that is the case, then the automaton is called a deterministic push down automaton. It is a PDA with the restriction that at most one move is defined from any reachable configuration. So, the next configuration, if exists, must be unique, but undefined cases are allowed. That is, you can come to a configuration from which no transition is defined, that is allowed, and such configurations are called dead configurations. So, dead configurations are allowed, but multiple next configurations are not allowed. So, suppose you have this transition, that means from the current state P on the next input simple small a and the top of stack simple capital X, there is a transition defined PAX. Then can you have P epsilon x in the same automaton, which is not to be a deterministic push down automaton? No, you cannot have, because then there is two different configurations possible depending on which one you apply, because you can decide to consume the next input and change to Q, or you can, without consuming that input, you can make this transition. So, this is not allowed. That means from a state for a next input simple, for an input simple and for a given stack simple, at most one transition. Even if you have one transition, then the epsilon transition is not allowed. And suppose no transition is allowed for this, then epsilon transition can be allowed. That is what I am trying to tell here. Unique epsilon move is allowed. For example, suppose your current state is P, next input simple is small a and top of stack simple is capital X, and you do not have a transition with LHS this, then you can have an epsilon transition. Why? Because then you will be having only a unique next configuration. Now, suppose in a deterministic push down automaton, you have two definitions for PAX, that is from the state P for the next input simple small a and the top of stack simple capital X. Suppose two transitions are defined, then they must be the same. We have to say Q must be same as R and alpha must be same as beta, because you will never have two different transitions. Okay, so they are essentially the same. And by definition, deterministic push down automata except by final state. Now, without loss of generality, we can assume, because we know that from the previous lecture, the acceptance criteria are equivalent. So, here you take it as final state acceptance, and we can see that the input tape needs to have a right hand marker for the PDA to be a deterministic one. So, you cannot just have the simples, but there must be a right hand marker. So, this is the right hand marker. Maybe we can see why. Consider this push down, this configuration of a push down automaton, and suppose you have this transition undefined. That means if the state is P and the next input simple is small b and capital A is on top of stack, and suppose that you have an epsilon transition for that. That is, if you are in P and capital A is on top of stack, without consuming an input, you can change your state to Q by retaining the symbol is what this transition is telling. Right? So, now no issue, because you only have a single next configuration. But see what happens if the input is completely processed and the read head is going after the last simple. And what is the configuration now? P is the state, A is on the top of stack, then this transition can be applied, right? So, what is the problem now? Now the problem is How will you accept? Suppose you want to now enter into a final state. Suppose you realize that the input can be accepted and you want to move to a final state, because final state acceptance is what we need. You need to have a transition, right? From P, without processing an input, if capital A is on top of stack, then you change your state into a final state, and it doesn't matter what you do with this stack, but you are just popping it. Okay, you need it, otherwise you cannot make a state change to accept this string. Now you can see that, see this is not allowed because you are not getting a non-determinism. See that there are two different next configurations now possible, right? From here you can either decide to change into Q or decide to change into F, which is not allowed. I think you are getting why a right end marker is required. Suppose a right end marker is there, you can say, suppose a right end marker is there, you can say if you are in the state P and next input is right end marker, that means you finished, then you jump into the final state. Okay, I think you are getting an example situation which demands the presence of a right end marker. So that is a requirement for a deterministic push down automata. Otherwise there could be multiple next configurations possible. Now we can try to have a deterministic push down automaton for this language. W reverse, in between there is a C. So it's set of all palindromes with an additional C in the middle. So this is a string in the language. You can see that this is ABB and this is the reverse of ABB, that is BBA. W and W reverse, and there is a C in between. So this is in the language. We can try to design a machine, and what you can do is you can try to remember these symbols on the stack. Maybe for a small a you push a capital A, and for a small b you push a capital B. That is what you can do. And when you see the middle symbol, without changing the stack content, you move on to the right side in a different state, and then you can see that B, if B is there, the last symbol here must be B. That means the top of stack symbol here must be a capital B. This is the logic that we can apply. Suppose you are starting here. This is the configuration. S is the state, small a is the input symbol, port is there on the stack. What you do, corresponding to this small a, you want to get capital A. So the RHS should be no state change. On the top of this spot, you put a capital A. So if you apply that transition, what will happen? Read head will come to this point, no state change, and you will get a capital A on the top of it. Yes, you applied that transition. Now what you need? You need a transition for SBA. Now can you tell me what transition you need? On the top of capital A, you need to push a capital B, and that's it. Remain in the state, take out A and push in BA, means A is also given back to the stack and above which a capital B is put. And if you apply this transition here, what will happen? The read head will move to the next symbol, B will come in the top of A. Now what is this transition now? SBB, which is not defined. So what you need? Can you tell me? Until you reach into C, you have to push a corresponding symbol. So here on top of capital B, you need one more B, because what you are getting as input is a small b. So this is the transition that you need, and if you apply, what will happen? B will be taken out and BB will be pushed in. and you will move to next simple. Now see, you are getting into the middle of the tape, that means you finished off W. So what you have to do, you have to move into a new state, because now I have to process the reverse of W, and I should not make any change in the stack content, because I need to match this BBA with this string. So what you do is, without changing the stack content, you change a state, say P. So B is taken out and B is pushed in. So no change effectively made. And if you apply, what will happen? State will be changed to P. You will come into this simple and no change in the stack content. This is what is happening. Now after this C, what you are doing is a matching between this simple and the corresponding capital letter here. Now you are having PB, capital B. So that means now you are getting a B, correspondingly previously here you had a small b. So you can just cancel them. What you do, you take out, remain in P and move right. Okay, remain in P, you take out B, no need to push in anything, and that's it. And what is next? P, B, B. That is this transition. Apply it again, you will move right. And not that applying this transition will take out this P. Now what? Again P, P, B. So you can apply that again. Now you are getting into a situation you need a transition for P small a capital A. What do you need? That means now you are getting a small a here, and correspondingly here you wanted to have a small a, then you are expecting to have capital A here, and that's exactly what you are getting. So you can pop off. Okay, if you apply, you will move right, and you are getting into the bottom simple, and now you need a transition this. That is, you are in state P and you are reading the right hand marker. That means you finished the input. Then suppose the string is in the language, then only bot must be there in the stack. That means the top of stack simple must be bot. That means, yeah, you can accept. So jump into a final state and pop off this simple. So you are accepting. And this is the transitions that you need for this particular input. But some other input may need few more transitions. One is this. While you see a capital A on the top of stack and you are processing a small a again in this part of the string, then this is what you should do. Similarly, if you are in S, you are getting a small a. When you have capital B on top of stack, then this is what you need. And here again, we got capital B on the top of stack when you moved into the simple C, but that can be a capital A also. So yeah, before that I missed another transition. What is it? Suppose you start with a small b here. You want to insert a capital B. That is what I do. Now the other transition that I was trying to tell. When you move into this cell, the stack top can be either B or A. That is what I am doing. Now I finished. So this is a deterministic push down automaton. You can verify that in every case a unique move is defined for any reachable configuration, and hence by definition it is a deterministic push down automaton. Sorry, I missed one more transition. What is it? Suppose I am giving an input string which is C alone. This is epsilon and W reverse is then also epsilon. For that I need this this transition. If you are in S, you are getting into C, while bot is the top of stack simple, meaning without processing anything in this part, you reached into C. What you can do is you can just move on to P without changing the stack content, and not that you cannot process any simple in the right side as well, because only bot is there. So neither A no B's can be processed after C. Now see that we have a deterministic push down automaton for this language, set of all palindromes where in the middle you have a small c, which tells you when you want to change your state, when you want to start popping or matching, whatever you call. But if you remove that c, the resulting language is the set of all even palindromes, which is going to be difficult for recognizing with a push down automata, and it is not to be a non-deterministic push down language. There is no deterministic push down automaton exists for accepting this language. Recall that we had a push down automata that is non-deterministic. You can see that when we changed into the right, we have used an epsilon transition, and that the machine should non-deterministically select when to apply. Or you can think about a PDA, and if you get a PDA, you can see that your PDA is not deterministic. Now see what can be the computation of a deterministic push down automaton. You start with this unique configuration for any input string W. The start state, entire input needs to be processed and only bought on the top of stack. And we know that in a deterministic push down automaton, only one next configuration is defined, and that is true always for every reachable configuration, and hence the computation is a linear sequence of states as opposed to a tree in the case of a non-deterministic push down automaton. So this is a linear sequence or a path, and an input is said to be accepted if the path ends in a final state. Not that checking whether a PDA accepts is very efficient here, because only one path is possible and you only have to simulate the PDA for how many times? The length of the input. Okay, but in the case of non-deterministic push down automaton, maybe you have to utilize an algorithm design strategy like backtracking. You try to go down the tree depth first, maybe, then when you realize that path is non-accepting, you go back and try to explore another path. So the natural design strategy coming to your mind is backtracking. That means after exploring a possibility, you backtrack, you erase what you did, go back and try to explore a different path. That is basically backtracking. Now with this we are coming to the last slide, where I am giving you an exercise problem for you to practice how you can design a deterministic push down automaton. Today we define deterministic push down automata, and the difference here is that from every reachable configuration we need at most one next configuration. So the next step is uniquely defined, and recall that undefined cases can be there or dead configurations are allowed, but multiple transitions are never allowed in a deterministic push down automaton. And we also have seen that for a non-deterministic push down automaton, the computation on a given input string in general can be modeled as a rooted tree. So there are many different paths possible, and the input is said to be accepted if one of the path is accepted. So in a systematic way, we may have to explore all the possible paths in the tree to see whether an input string is accepted or not. So, it is not a very efficient process because we have to explore all paths in the tree in the worst case. But in the case of a deterministic finite state automaton, deterministic push down automaton, the execution can be modeled as a path or a linear sequence of states. So, only one sequence of length n, where n is the length of the input, needs to be simulated to decide whether the input is accepted or not, and hence you are getting a linear algorithm. It is the number of simulations required or number of steps in the steps required in the simulation of that push down automaton is the length of the input string. So, in that way, if we are having a deterministic push down automaton, then checking whether a given string is in the language or not is very efficient. And we also have seen a language which is a set of all even length palindromes for which there is not to be no deterministic push down automata possible. So, that is giving us a counter example that for checking whether push down automaton and non-deterministic push down automaton are of the same power or not. They are not, because we at least have this language WW reverse for which there is no deterministic push down automaton exists. Thank you.